Welcome. Today, we begin a systematic study of the industrial life cycle and mechanical synthesis of the standard writing instrument. This is the complete technical history of the pencil. Please subscribe to the channel and like this video after waking up in the morning. Sweet dreams. The conceptualization of the writing instrument begins with the slow, multi-decadal accumulation of biological matter within a controlled forest environment. The incense cedar, a species selected for its specific cellular density and straightness of grain, grows within a high-altitude ecosystem where the environmental variables dictate the thickness of the annual growth rings. As the seasons fluctuate, the tree absorbs moisture and nutrients through its extensive root system, transporting these elements through the xylem and phloem layers. The lignin and cellulose fibers are deposited in a concentric fashion, creating a structural lattice that will eventually serve as the protective housing for the graphite core. This biological process occurs in a state of relative silence, interrupted only by the occasional shift in the surrounding soil or the movement of the atmospheric gases through the needle-like foliage of the coniferous structure. When the timber has reached a state of maturity suitable for industrial utilization, the process of mechanical harvesting is initiated. The machinery employed for this task is designed to exert significant pressure upon the trunk of the tree, utilizing a heavy-duty hydraulic arm that stabilizes the biological column before the cutting blade begins its rotation. The movement of the blade through the wood fibers involves a complex interaction between the steel teeth and the organic polymers of the tree. As the blade penetrates the bark, the cellular structure is interrupted, releasing a fine mist of moisture and volatile organic compounds into the surrounding air. The tree is then lowered in a controlled arc, its weight supported by the mechanical fingers of the harvester, and the lateral branches are removed through a sequential shearing action. The resulting logs are then organized into uniform piles, awaiting the arrival of the transport vehicles that will move them toward the primary processing site. Simultaneously, the procurement of the marking medium begins deep within the crust of the earth, where the geological pressure of past eras has transformed carbonaceous matter into crystalline graphite. This mineral is found in veins of metamorphic rock, often embedded within layers of schist or gneiss. The extraction of the raw graphite involves the removal of the surrounding rock through the application of mechanical force and, in some cases, the use of industrial-grade pneumatic drills. The drills vibrate at a high frequency, creating microfractures in the rock face that allow the graphite-bearing ore to be dislodged in large, irregular fragments. These fragments are collected by heavy machinery and placed upon a series of conveyor belts that wind through the underground tunnels. The sound of the conveyor belt is a constant, low-frequency hum that resonates against the stone walls, as the rubberized surface of the belt carries the mineral weight toward the surface. Once the timber logs arrive at the sawmill, they are subjected to a process of debarking. This involves the use of rotating mechanical drums that utilize friction and centrifugal force to strip away the outer protective layer of the tree. The bark is dislodged in large, rough sections, exposing the pale, fragrant sapwood underneath. This sapwood is then examined for any visible defects, such as knots or parasitic incursions, that might compromise the structural integrity of the final pencil. The log is then positioned upon a carriage that moves with precise incremental steps toward a massive band saw. The saw blade, a continuous loop of tensioned steel, moves at a high velocity, creating a high-pitched vibration as it encounters the resistance of the wood. The log is sliced into thick planks, which are then stacked in a staggered formation to allow for the initial stage of atmospheric stabilization. The transition of the graphite ore into a usable mineral powder involves the use of primary and secondary crushing units. The raw ore is fed into a cavernous chamber where large steel jaws move in a reciprocating motion, exerting immense pressure upon the mineral fragments. This pressure causes the rock to shatter, breaking it down into smaller, more manageable pieces. The resulting material is then passed through a series of vibrating screens that sort the fragments by their physical dimensions. The smaller pieces are directed toward the secondary mill, while the larger fragments are recycled back into the primary crusher for further reduction. The wooden planks, now organized into stacks, must undergo a process of seasoning to reduce their internal moisture content. This seasoning is a critical phase, as the presence of excess water within the cellular structure would lead to warping and shrinkage during the subsequent manufacturing stages. The planks are placed within a climate-controlled kiln, where the movement of warm air is managed by a series of large industrial fans. The fans operate with a monotonous rhythmic drone, moving the air in a constant laminar flow. The temperature inside the kiln is raised in a slow, incremental fashion, ensuring that the wood dries evenly from the core to the perimeter. In the graphite refinement facility, the crushed mineral is subjected to a process of froth flotation. This involves placing the graphite fragments into a large water-filled tank where specific chemical reagents are introduced. These reagents alter the surface tension of the graphite particles, allowing them to attach to air bubbles that are pumped into the bottom of the tank. As the bubbles rise to the surface, they carry the graphite with them, forming a thick, dark froth that is skimmed away by a mechanical paddle. The heavier impurities, such as silica and iron, sink to the bottom of the tank and are removed as waste. The collected froth is then washed and dried, resulting in a fine crystalline powder that possesses a high degree of purity. The movement of the skimming paddle is slow and consistent, clearing the surface of the tank in a repetitive circular motion. The preparation of the clay, which serves as the binding agent for the graphite, involves its own sequence of mechanical and chemical refinement. The raw clay is excavated from sedimentary deposits and transported to the facility, where it is mixed with water to form a thick, viscous slurry. This slurry is then passed through a series of hydrocyclones, which utilize centrifugal force to separate the fine kaolinite particles from the larger quartz and mica fragments. The slurry rotates within the conical chamber of the hydrocyclone, with the lighter clay particles moving toward the center and being discharged through the top, while the heavier impurities are forced against the walls and exit through the bottom. The sound of the hydrocyclone is a steady, high-velocity rush of liquid as the centrifugal force operates on the mineral suspension. The refined wood planks are then moved to the ripping station, where they are cut into thinner sections known as slats. This process involves the use of multiple circular saw blades that are mounted on a single shaft. As the wood is fed into the machine, the blades create a series of parallel cuts, dividing the wood into slats of a specific width and thickness. The movement of the wood through the ripping station is assisted by a set of drive rollers that exert a constant pressure upon the surface of the plank, ensuring a steady rate of progress. The sawdust generated during this operation is immediately captured by a vacuum system that pulls the fine particles away from the blades and into a centralized collection bin. The graphite powder and the refined clay are then stored in separate silos, awaiting the arrival of the mixing phase. These silos are large cylindrical structures that protect the mineral contents from atmospheric humidity and contamination. The movement of the powder into and out of the silos is managed by a system of pneumatic tubes and rotary valves, which use compressed air to transport the material through the facility. The air moves with a dull, hollow hiss, carrying the fine dust through the labyrinth of pipes. The state of the raw materials at this point is one of potential, as the biological fibers of the cedar and the mineral crystals of the graphite and clay have been isolated and refined, ready to be reintegrated into a single functional object. The transition of the refined graphite and clay from their respective storage silos into a unified functional composite marks the beginning of the core manufacturing phase. This process is initiated by the simultaneous release of the mineral powders from the conical bases of the silos. The powder descends through a series of enclosed chutes, its movement facilitated by the constant vibration of the metal walls, which prevents the fine particles from adhering to the interior surfaces. The two materials converge in a large industrial mixing vessel where the initial dry blending begins. The blades of the mixer, heavy and forged from reinforced steel, rotate in a slow circular pattern, lifting the mineral mass and allowing it to cascade back onto itself. This repetitive motion ensures that the graphite crystals and the clay silicates are distributed evenly throughout the volume of the chamber, creating a dry, gray-toned powder that lacks any visible streaks or clusters. Once the dry homogenization is complete, the process of hydration is introduced to transform the powder into a malleable, plastic state. Deionized water is dispensed into the mixing chamber through an overhead manifold, which releases the liquid in a fine, controlled spray. The water droplets interact with the surface of the clay particles, penetrating the microscopic spaces between the mineral flakes through capillary action. As the mixer continues its rhythmic rotation, the powder begins to clump together, gradually shifting from the loose amorphous state into a thick, viscous paste. This physical transformation involves a significant increase in the internal resistance of the material, requiring the motor of the mixer to maintain a steady, powerful torque. The sound of the mixing process changes from a dry, shifting rustle to a wet, heavy thudding as the paddles force the dense mass through the center of the vessel. The homogenization of this paste is further refined through a process of high-shear mechanical agitation. The blades of the mixer move in a planetary motion, rotating on their own axes while simultaneously orbiting the center of the mixing bowl. This complex movement subjects the paste to intense shearing forces, which break down any remaining aggregates of clay or graphite. At the molecular level, the water acts as a lubricant, allowing the flat graphite flakes to slide into the spaces created by the hydrating clay matrix. The goal of this stage is to ensure that every individual graphite particle is completely encapsulated by a thin layer of clay, a condition that is essential for the structural integrity of the final lead. The surface of the paste takes on a dark, reflective sheen, indicating that the water has been thoroughly integrated into the mineral structure. To ensure that the final writing core is free from internal defects, the paste must undergo a process of vacuum degassing. This is achieved by sealing the mixing chamber and activating a high-power vacuum pump. As the atmospheric pressure within the vessel is reduced, the air that was entrapped within the paste during the mixing process begins to expand and rise to the surface. Small bubbles form and collapse in a continuous rhythmic cycle, releasing the captured gases into the vacuum line. The removal of these air pockets is vital, as even a microscopic void within the paste could lead to a catastrophic fracture when the pencil is later subjected to the pressure of a sharpener or the hand of a user. The sound of the vacuum pump is a steady mechanical drone that underlies the shifting movements of the paste within the chamber. The degassed paste, now possessing the consistency of heavy dough, is moved toward the extrusion press. This machine utilizes a large hydraulic ram to force the material through a precisely shaped aperture known as a die. The movement of the ram is slow and deliberate, exerting a constant, unrelenting pressure upon the mass of paste. As the material is compressed within the cylinder, it is forced toward the die at the far end. The die is a small disc-shaped component made from a synthetic gemstone or an extremely hard metallic alloy, featuring a single perfectly circular hole at its center. The internal geometry of this hole is tapered to compress the paste as it passes through, ensuring that the resulting filament is dense and uniform in its cross-section. As the graphite filament emerges from the die, it appears as a continuous wet string that is supported by a series of moving rollers. The filament is characterized by its smooth, dark surface and its relative flexibility in its wet state. It moves along the conveyor at a steady velocity, passing under a high-speed cutting mechanism. This mechanism features a thin, tensioned blade that moves in a vertical, reciprocating motion, slicing the continuous string into individual segments of a standardized length. The timing of the cut is synchronized with the speed of the conveyor, ensuring that each segment is identical to the one before it. The sound of the cutter is a sharp, repetitive snap that occurs at regular intervals, marking the transformation of the continuous string into discrete writing cores. These segments, referred to as green leads, are then collected and organized onto flat metal trays. The leads must be handled with extreme care as their high moisture content makes them susceptible to deformation or breakage. The trays are moved into a drying tunnel where the ambient temperature is gradually increased to remove the integrated water. This drying process involves the slow migration of moisture from the core of the lead toward the surface, where it is carried away by a laminar flow of warm air. As the water evaporates, the clay matrix begins to contract, pulling the graphite particles closer together and increasing the overall density of the lead. The leads lose their reflective sheen and become matte, gray to black appearance, becoming brittle and rigid as they reach their dry state. The final structural transformation of the leads occurs within a high-temperature kiln. The dry leads are placed within sealed containers to protect them from the reactive gases of the atmosphere and are subjected to an intense thermal cycle. As the heat within the kiln rises, the clay binder undergoes a process of vitrification. The chemical bonds within the clay silicates are altered, causing the material to fuse into a hard ceramic-like structure that permanently locks the graphite flakes into place. This process is characterized by the slow, steady radiation of heat from the kiln walls, which permeates the containers and reaches the center of each lead. The atmosphere inside the kiln is kept inert, preventing the carbon in the graphite from reacting with oxygen. Once the vitrification is complete, the kiln is allowed to cool in a slow, controlled manner. The thermal energy is dissipated through the insulated walls of the chamber, and the leads are brought back to a temperature that allows for mechanical handling. This cooling phase is essential to prevent the leads from cracking due to sudden thermal contraction. When the leads are finally removed from the kiln, they have achieved their final state of hardness and durability. They are no longer malleable or brittle in the sense of the green state. They are now semi-ceramic rods that possess the specific marking qualities required for a writing instrument. The final stage of the core manufacturing involves a process of impregnation with molten wax. The hardened leads are submerged in a vat of liquid paraffin or carnoa wax, which is kept at a constant, elevated temperature. The liquid wax penetrates the microscopic pores within the ceramic graphite structure, filling the voids that were created when the water evaporated during the drying phase. This impregnation serves to lubricate the lead, ensuring that it glides smoothly across the paper and reduces the friction generated during the writing process. The leads are then removed from the wax bath and allowed to cool, with the excess wax being spun away in a centrifugal drum. The resulting cores are now finished, possessing the dark, consistent quality that is necessary for their integration into the wooden housing. The seasoned wood slats, having achieved a state of internal equilibrium after their time in the tempering sheds, are now ready to be transformed into the structural halves of the final instrument. Each slat, characterized by the straight grain and aromatic fragrance of the incense cedar, is introduced into a high-speed profiling machine. This mechanical transition begins as the slats are moved from their organized stacks by a series of suction-based arms that lift each piece with a rhythmic, pulsating motion. The slats are placed onto a horizontal conveyor where they are gripped by a set of rubberized drive rollers. These rollers exert a constant downward force, ensuring that the wood remains perfectly flat as it encounters the first set of rotating cutters. The movement of the wood into the machine is accompanied by a continuous low-pitched vibration that resonates through the heavy metal frame of the profiling unit. Inside the machine, a set of high-velocity spindles, rotating at a frequency that produces a persistent high-pitched whine, are fitted with precisely ground milling heads. As the slat passes under these heads, the steel teeth of the cutters begin to carve a series of parallel, semicircular channels into the surface of the wood. This process involves the systematic removal of cellulose fibers and lignin, which are ejected from the cutting zone in the form of fine dust and small curled shavings. The geometry of these channels is critical, as each must be exactly half the diameter of the vitrified graphite leads that were prepared in the previous phase. The interior surface of the grooves is rendered smooth by the speed of the cutters, appearing almost polished as the wood cells are sheared with mechanical precision. The scent of the wood is intensified at this stage, released by the heat generated by the friction of the blades. The slats, now featuring their characteristic grooved profile, emerge from the milling station and are immediately moved toward the adhesive application module. This unit consists of a rotating drum that is partially submerged in a reservoir of liquid polyvinyl acetate dispersion. As the drum rotates, it picks up a thin, uniform film of the white adhesive, which is then transferred to the surface of the moving slat. The adhesive is forced into the grooves and across the flat lands between them by the pressure of the application roller. The consistency of the liquid is maintained at a level that allows it to wet the wood fibers thoroughly without flowing beyond the edges of the slat. The movement of the roller is a constant circular motion, ensuring that the distribution of the adhesive remains identical from one slat to the next. Simultaneously, the finished graphite leads are retrieved from their storage canisters and loaded into a vertical hopper. This hopper utilizes a subtle vibrating action to align the leads, ensuring that they are oriented parallel to the direction of the assembly line. At the bottom of the hopper, a timed release mechanism allows the leads to descend one by one into the waiting grooves of the adhesive-coated slat. This integration is managed by a series of mechanical fingers or a vacuum-assisted manifold that places the leads with a soft, repetitive thud. Each lead must be seated perfectly within its designated channel, submerged halfway into the wet adhesive. The coordination between the movement of the slat and the placement of the leads is a display of synchronized mechanical timing occurring with a regularity that defines the pace of the production environment. Once the leads have been integrated into the bottom slat, the cover slat is prepared to complete the assembly. This second slat, which has also been milled with identical grooves and coated with adhesive, is moved by a mechanical inverter. This arm captures the slat and rotates it exactly 180 degrees, positioning it directly above the lead-bearing slat. The two halves are brought together, with the grooves of the top slat descending to encapsulate the upper half of the graphite leads. This meeting of the two wooden surfaces creates a laminated block, often referred to as a sandwich. The alignment must be absolute. The lateral guides of the machine ensure that the edges of the two slats are flush, preventing any internal shift that would result in an off-center core. The assembled blocks are then moved toward the primary pressing station, where they are subjected to a massive, unrelenting hydraulic force. The blocks are stacked in large batches and placed between the heavy, flat platens of the press. As the hydraulic fluid is pumped into the cylinders, the platens converge, exerting a pressure that forces the two wood slats into intimate contact. This pressure causes the excess adhesive to be squeezed out from the edges of the block, where it is removed by a set of stationary scrapers. The duration of the press cycle is determined by the time required for the adhesive to begin its initial polymerization, creating a bond that is stronger than the wood fibers themselves. The sound of the press is a heavy, rhythmic groan as the metal structure absorbs the tension of the hydraulic load. Inside the press, the temperature may be slightly elevated to facilitate the movement of the water from the adhesive into the surrounding wood. This interaction is a slow molecular process as the polyvinyl acetate chains begin to interlock with the cellulose structure of the cedar. The wood, in turn, absorbs a small amount of moisture, causing a temporary localized swelling along the glue line. This internal tension is managed by the constant pressure of the platens, ensuring that the block remains dimensionally stable as the bond solidifies. The environment around the press is characterized by the hum of the hydraulic pumps and the occasional hiss of released air as the cycle completes and the platens retract. After exiting the press, the blocks are moved to a stabilization area where they must rest for an extended period. During this time, the internal moisture that was introduced by the adhesive is allowed to redistribute evenly throughout the volume of the block. This redistribution is essential to prevent the wood from warping or cracking during the subsequent shaping stages. The blocks are stored on open racks, allowing for a natural, laminar flow of air to circulate around each unit. The state of the blocks at this point is one of monolithic stability. The two separate slats and the 8 graphite leads have been transformed into a single composite object that possesses the structural properties of a solid piece of timber with a multi-cored interior. The surface of the blocks is then subjected to a preliminary trimming operation. This involves the use of 2 side-mounted saws that remove the uneven edges where the 2 slats met. The blades move with a steady, high-velocity rotation, creating a clean, perpendicular edge that facilitates the precise feeding of the blocks into the next machine. The sound of the trimming saws is a sharp, consistent buzz as each block passes through the cutting zone. The resulting rectangles are uniform in their dimensions, with the dark ends of the graphite leads clearly visible at each end of the block, perfectly centered within the wood and glue matrix. As the blocks are stacked and moved toward the next department, the mechanical process of assembly is complete. The fragile, vitrified leads are now protected by the dense aromatic fibers of the cedar, and the bond between the materials has achieved its full structural strength. The blocks possess a tactile weight and a sense of solidity that was absent when the components were separate. They await the final transformation where the monolithic block will be disaggregated into the individual hexagonal forms that are recognizable as pencils. The atmosphere of the facility at this stage is one of steady industrial progress as the movement of the material follows a predetermined path through the labyrinth of machines. The transition of the monolithic laminated blocks into individual writing units represents a fundamental shift in the mechanical state of the material. This stage of the process, occurring within the high-velocity shaping environment, involves the controlled destruction of the block's rectangular geometry in favor of a series of symmetrical hexagonal cylinders. The blocks, having achieved a state of internal structural stability, are fed into the intake manifold of the shaping machine. This movement is facilitated by a set of vertical hopper rails that guide the blocks downward, where a reciprocating pneumatic pusher initiates their entry into the primary drive rollers. These rollers, surfaced with a high-friction polymer to prevent slippage, grip the upper and lower faces of the block, propelling it toward the high-speed rotational cutters at a constant, unvarying velocity. The atmosphere within this section of the facility is dominated by the steady mechanical pulse of the intake system and the underlying vibration of the heavy cast-iron base of the shaping unit. Inside the shaping chamber, the transformation is executed by a dual spindle configuration consisting of an upper and a lower cutter head. These heads are fitted with multiple sets of knives, ground to a specific profile that corresponds to the three facets of a half hexagon. As the block passes under the upper cutter head, which rotates at a frequency that transcends the audible range into a persistent atmospheric hum, the knives begin to shear away the cedar fibers. This first pass carves the upper profile of the 8 individual pencils, removing approximately half of the wood's thickness. The wood cells are severed with such rapidity that the resulting surface appears momentarily scorched by the heat of the friction before being cooled by the constant airflow of the extraction system. The removed material is immediately converted into fine chips and airborne dust, which are pulled away from the cutting zone by a powerful vacuum, creating a localized laminar flow of air that keeps the interface between the blade and the wood free of debris. Immediately following the upper cut, the block encounters the lower cutter head, which is positioned in a mirrored orientation. This second set of knives rotates in the opposite direction, carving the bottom 3 facets of the 8 pencils. The critical mechanical event occurs at the horizontal midline of the block, where the path of the lower knives meets the path of the upper knives. At the exact moment of convergence, the structural bond of the original laminate is severed, and the monolithic block ceases to exist. In its place, 8 individual hexagonal rods emerge from the cutter assembly. This transition is a continuous fluid motion as the pencils are pushed forward by the preceding block, maintaining a tight end-to-end formation that ensures the stability of the cut. The sound of the separation is a sharp, overlapping series of mechanical notes, muffled by the sound-dampening enclosures of the machine. The individual hexagonal pencils, now in their raw, unsanded state, are diverted onto a lateral conveyor that organizes them into a single-file row. Although the high-speed cutters produce a profile that is geometrically accurate, the surface of the wood retains a series of microscopic cutter marks, small rhythmic indentations left by the rotating knives. These marks must be removed to ensure a surface that is receptive to the subsequent application of lacquer. The pencils are moved toward the first of several abrasive refinement stations. This station utilizes a series of tensioned sanding belts that oscillate in a direction perpendicular to the movement of the pencils. The first belt is surfaced with a coarse mineral abrasive designed to level the facets and remove the primary irregularities left by the shaping process. The friction of the belt against the wood generates a fine reddish-colored dust, which is carried away by a secondary vacuum duct. As the pencils progress through the sanding module, they are subjected to a process of rotation that ensures each of the 6 facets is treated with the same degree of abrasive force. The mechanical guides within the sander use a series of small star-shaped wheels to turn the pencils exactly 60 degrees between each sanding head. This rotation is synchronized with the forward movement of the conveyor, creating a repetitive mechanical dance as the pencils shift and turn under the abrasive belts. The second sanding station utilizes a medium grit belt, which further refines the surface by shearing away the smaller fibers that were lifted by the coarse grit. This stage is essential for closing the grain of the wood, preparing the cellular structure of the cedar to absorb the primer layers without excessive swelling or surface distortion. The final stage of abrasive refinement involves the use of a very fine grit belt, which provides a polished, almost reflective quality to the raw wood facets. At this point, the movement of the belt is less about material removal and more about the surface homogenization of the lignin and cellulose. The heat generated during this final task is minimal, and the sound is a soft, continuous shoosh that contrasts with the aggressive grinding of the earlier stages. The surface of the pencil becomes tactily smooth, with the grain of the cedar appearing as a subtle, linear pattern that flows along the length of the hexagonal cylinder. The ends of the graphite core are now visible as dark circular apertures at each end of the hexagonal rod, perfectly centered within the wood housing. Throughout the shaping and sanding operations, the management of wood dust is a constant underlying process. The facility utilizes a centralized dust collection system that pulls air from every machine through a network of galvanized steel pipes. The movement of this air is a persistent hollow roar that fills the upper reaches of the ceiling. The dust is carried to a large external baghouse where it is separated from the air by a series of fabric filters. The air is then recirculated or exhausted, while the collected cedar dust is moved by a screw conveyor into a storage bin. This constant extraction is vital not only for the cleanliness of the final product, but also for the longevity of the machine bearings and the safety of the mechanical environment. The quality of the sanded pencils is monitored by a series of non-contact sensors that verify the dimensional accuracy of the hexagonal profile. These sensors use light beams to measure the distance between the parallel facets, ensuring that the diameter of the pencil remains within a strict tolerance. If a pencil is detected with a deviation, perhaps due to a slight misalignment of the sanding belt or a variation in the density of the wood, it is automatically diverted from the main line by a pneumatic gate. The rejected unit is collected in a separate bin for reclamation, while the remaining pencils continue their progress toward the next phase of the production cycle. The movement of the gate is a quick, decisive hiss of air that interrupts the steady flow of the conveyor. At the conclusion of the sanding process, the pencils are oriented so that their ends are flush and their facets are aligned. They are loaded into large rectangular crates that are designed to protect the raw wood from atmospheric humidity and physical impact. The weight of the crates increases as they are filled, moved by an automated palletizer that stacks them with mechanical regularity. The pencils at this stage possess a pale, natural color and a strong aromatic scent that permeates the surrounding area. They are now finished in terms of their physical geometry, having been transformed from a solid block of laminated materials into a collection of individual, precisely shaped and smoothly refined hexagonal units. The atmosphere of the facility as the crates are moved toward the coating department is one of quiet, industrial readiness. The mechanical energy of the shaping and sanding units is replaced by the steady rolling sound of the transport carts as they move along the polished concrete floor. The pencils, though still lacking their final color and functional components, have achieved their definitive form. They represent the successful integration of mineral and biological materials into a single cohesive geometry, ready to receive the chemical layers that will provide their aesthetic and protective finish. The process continues with an unyielding regularity, as each crate is logged into the tracking system and positioned for the next stage of its transformation. The movement of the hexagonal cedar rods from the shaping and sanding department into the coating facility represents the first stage of chemical surface modification. This transition occurs within a strictly regulated environment where the ambient temperature is stabilized to prevent any rapid expansion or contraction of the wood fibers. The individual pencils are extracted from their transport crates by an automated vacuum gantry, which utilizes a series of small rubber suction cups to lift the units in groups of 50. These units are then deposited onto a vibrating alignment tray that funnels them into a single file orientation. The pencils form a continuous end-to-end line as they are gripped by a set of drive rollers and propelled toward the primary coating module. The atmosphere in this section of the plant is characterized by a faint, persistent scent of volatile organic compounds and the steady rhythmic clicking of the feeder mechanism. The primary coating material, designated as the sealer or primer, is a high solid suspension designed to neutralize the natural absorption characteristics of the incense cedar. The chemical composition of this liquid includes nitrocellulose resin, a blend of plasticizers, and a high concentration of titanium dioxide to provide the necessary opacity. The preparation of the primer occurs in a separate mixing room where the ingredients are combined in a large stainless steel vessel. A high shear impeller rotates within the vessel, creating a vortex that ensures the uniform distribution of the white pigment particles throughout the resin base. The viscosity of the primer is monitored every 30 minutes using a flow cup. The time required for a specific volume of the liquid to exit the cup through a calibrated orifice is measured in seconds. This measurement is vital, as any deviation in viscosity would result in an uneven film thickness on the surface of the pencil. The application of the primer is executed through a process known as longitudinal extrusion coating, or more commonly, the wiper method. As the continuous line of pencils enters the coating module, they pass through a small pressurized reservoir filled with the white primer. Each pencil is completely submerged in the liquid, ensuring that all 6 facets and the ends are thoroughly wetted. The critical mechanical event occurs at the exit of the reservoir, where the pencil passes through a precision-cut rubber die, or wiper. This die is manufactured from a highly elastic synthetic polymer and features an aperture that is slightly smaller than the hexagonal diameter of the pencil. As the pencil is forced through the die, the rubber conforms to the hexagonal profile, wiping away the excess primer and leaving a thin, wet film that is measured in micrometers. The physics of this wiping process involve a delicate balance between the elasticity of the rubber and the surface tension of the primer. The die must exert enough pressure to remove the surplus liquid while maintaining a consistent film that fills the microscopic pores of the wood. This action creates a smooth white surface that serves as the foundation for the subsequent color layers. The sound of the pencils passing through the rubber dies is a repetitive, high-pitched squeak that coincides with the movement of each unit. The wet pencils, now appearing as matte white hexagonal rods, emerge from the coating module and are immediately transferred onto a wide, flat conveyor belt that leads into the primary drying tunnel. The drying tunnel is a long, enclosed structure divided into several distinct thermal zones designed to facilitate the controlled evaporation of the solvents from the primer film. The first section is the flash-off zone, where the pencils are exposed to a laminar flow of ambient air. This movement of air is managed by a series of centrifugal fans that pull the solvent vapors away from the surface of the pencils and into a centralized filtration system. During this phase, the most volatile components of the solvent blend begin to evaporate, causing the primer film to set or lose its initial fluidity. The speed of the conveyor is synchronized with the evaporation rate to ensure that the film does not develop bubbles or surface irregularities known as pinholes. As the pencils progress into the second and third zones of the tunnel, they encounter a series of infrared heating elements. These elements emit thermal energy at a specific wavelength that is absorbed by the primer film, increasing its temperature and accelerating the removal of the remaining solvents. This process is monitored by non-contact infrared sensors that transmit the surface temperature of the pencils to a central controller. The temperature is raised in a slow, incremental fashion to prevent the wood from releasing internal moisture, which would cause the primer to blister. The movement of the pencils through the tunnel is a slow, unvarying progression, with the conveyor belt moving at a constant velocity that ensures each unit receives the same amount of thermal exposure. Inside the drying tunnel, the air is continuously recirculated through a series of HEPA filters to remove any airborne particulates that could settle on the wet primer. The sound of the drying process is a steady, low-frequency roar produced by the large fans and the movement of the air through the ductwork. The chemical transition of the primer from a liquid to a solid state involves the formation of a dense polymer network as the nitrocellulose resin hardens. By the time the pencils reach the end of the tunnel, the primer has achieved an initial cure, becoming hard and dry to the touch. The pencils emerge from the tunnel and are automatically reorganized into groups where they undergo a light mechanical brushing to remove any nibs or dust particles that may have adhered to the surface during the drying phase. The entire priming cycle is typically repeated a second time to ensure a perfectly opaque and level surface. This involves recirculating the pencils back to the start of the coating line, where they pass through an identical reservoir and dye assembly. The second layer of primer fills any remaining irregularities and builds up the film thickness to the required specification. The repetitive nature of this process is fundamental to the quality of the final finish. Each layer is a mirror image of the one before it, applied with the same mechanical regularity. The pencils, now twice primed, possess a uniform, stark white appearance that completely obscures the natural grain and color of the cedar wood. The management of the solvent vapors is a critical environmental aspect of the coating department. The air that is extracted from the drying tunnels is routed to a thermal oxidizer, where the solvent molecules are broken down at high temperatures into carbon dioxide and water vapor. This process is essential for maintaining air quality within the facility and complying with environmental regulations. The movement of the vapors through the extraction pipes is a constant, invisible flow that mirrors the movement of the pencils on the conveyor belt. The efficiency of the recovery system is monitored by a series of gas sensors that provide a continuous readout of the VOC concentrations. At the conclusion of the priming and drying stages, the pencils are collected in large, oriented stacks. They have been transformed from raw, sanded wood units into chemically sealed white hexagonal rods. The surface of the pencils is now non-porous and ready to receive the decorative color layers that will provide their final aesthetic identity. The atmosphere of the facility at this stage is one of clinical efficiency, as the stark white pencils move through the clean room environment of the coating department. They represent a state of intermediate completion, where the structural work of the previous chapters has been encapsulated by a functional polymer barrier. The process continues without interruption as the next batch of pencils enters the alignment tray, ready to begin its own sequence of submersion, wiping, and evaporation. The quality of the primed surface is verified by an automated vision system that utilizes high-resolution cameras to scan the facets of each pencil as it exits the drying tunnel. The system looks for any variations in color or surface texture that could indicate a failure in the coating or drying process. If a defect is detected, the position of the pencil is logged and it is automatically removed from the line at the next transfer point. This constant, high-speed inspection ensures that only units with a perfect primer base are allowed to proceed to the color application stage. The mechanical regularity of the inspection, the coating, and the drying forms a continuous loop of production that defines the daily operation of the finishing department. The transition of the stark white primed hexagonal rods into the color application phase represents a shift from structural preparation to the establishment of the final aesthetic identity. This stage of the process occurs within a specialized section of the facility where the air is filtered to a high degree of purity to prevent the deposition of microscopic particulates onto the wet surfaces. The pencils, now organized in their white state, are moved by a series of mechanical arms that utilize low-pressure vacuum suction to lift and position them onto a high-speed feeder track. This track aligns the units end to end, forming a continuous, unbroken line of wood and graphite that moves toward the primary color reservoirs. The atmosphere here is thick with the rhythmic, mechanical clicking of the alignment gates and the underlying hum of the pumps that maintain the circulation of the pigmented liquids. The color lacquer, typically a vibrant shade of yellow, is a complex chemical suspension consisting of finely ground pigments dispersed within a nitrocellulose resin base. The preparation of this liquid involves a lengthy homogenization process in large stainless steel tanks located in an adjacent mixing room. Inside these tanks, heavy industrial impellers rotate continuously, preventing the pigment particles from settling at the bottom and ensuring that the color remains consistent throughout the entire production run. The liquid possesses a specific flow characteristic, carefully calibrated to allow it to spread evenly across the hexagonal facets without accumulating at the corners or edges. The movement of the yellow lacquer through the delivery pipes is a constant pressurized flow, moving from the bulk tanks to the smaller machine reservoirs where the pencils are submerged. As the line of pencils enters the color module, they pass through a pressurized chamber where the yellow lacquer is applied through a multi-point injection system. Each pencil is completely enveloped in the liquid, which fills every microscopic indentation that may have remained after the priming stage. The mechanical heart of this operation is the set of rubber extrusion dies, similar to those used in the priming stage, but adjusted for the specific rheology of the colored enamel. As the pencil is propelled through the die, the elastic material of the gasket exerts a uniform pressure against the hexagonal surface, stripping away the excess liquid and leaving behind a wet film of uniform thickness. This action is repeated several times in succession, as a single coat of yellow is often insufficient to provide the deep, saturated opacity required for a professional-grade instrument. The pencils emerge from the first color station and are immediately carried into a primary drying tunnel. This tunnel is a cavernous, heated environment where the movement of air is the primary force of evaporation. Large centrifugal blowers pull air from the room, heat it through a series of thermal exchanges, and push it in a laminar flow over the moving pencils. As the solvents in the lacquer begin to flash off, the surface of the pencil shifts from a glossy liquid state to a tacky semi-solid state. The sound of the airflow within the tunnel is a constant, hollow roar, echoing off the insulated metal walls. The conveyor belt, a mesh of heat-resistant fibers, carries the pencils at a slow, unvarying pace, ensuring that each unit receives a consistent duration of thermal exposure. The solvents, once evaporated, are captured by a high-capacity extraction system and routed to the thermal oxidizer for environmental processing. The process of color application is iterative. After emerging from the first drying tunnel, the pencils are redirected through a second and often a third color module. Each subsequent pass adds another layer of pigment, building up the depth of the yellow and ensuring that no white from the primer remains visible. This repetition is a cornerstone of the mechanical logic of the facility. The machines operate in a continuous loop, performing the same sequence of submersion, wiping, and drying over and over again. The alignment of the pencils remains end-to-end, creating a seemingly infinite yellow ribbon of wood that flows through the heart of the coating department. The precision of the rubber dies is checked on regular intervals, as the friction of the moving pencils gradually wears down the elastic aperture, which could lead to an increase in film thickness and an uneven finish. Following the final pigmented layer, the pencils are subjected to the application of a clear, protective top coat. This liquid is a transparent version of the nitrocellulose lacquer, formulated without pigments but with a higher concentration of resins and gloss-enhancing agents. The application method is identical to the color stages, with the pencils passing through a clear coat reservoir and a final set of rubber wipers. The liquid is notably more viscous than the colored enamel, requiring a different pressure setting in the reservoir to ensure a smooth, bubble-free application. The final drying tunnel is longer and operates at a more controlled temperature gradient than the previous ones. This is necessary to allow the clear coat to level out perfectly before it hardens, a process driven by the surface tension of the liquid lacquer. As the pencils move through the tunnel, they are exposed to infrared radiation that penetrates the layers of coating, ensuring that the entire film dries from the wood interface outward. This prevents the formation of orange peel or other surface irregularities that could compromise the clarity of the finish. The movement of the air in this final tunnel is slower and more filtered, as any dust particles settling on the wet clear coat would be permanently embedded in the final product. Upon exiting the final drying stage, the pencils pass through a cooling zone where they are exposed to a gentle flow of ambient filtered air. This reduces the surface temperature of the lacquer, allowing it to achieve its final shore hardness. The tactile quality of the pencils change as they cool. The tacky warmth of the drying tunnel is replaced by a cold, hard, and exceptionally smooth surface. The edges are sharp and well-defined, and the yellow color appears deep and uniform under the protective transparent layer. The pencils are then automatically reorganized into large oriented stacks where they are held in a buffer zone for a final period of atmospheric stabilization. This rest period allows any trace amounts of residual solvent to migrate out of the film, ensuring that the pencils will not stick to one another during the subsequent packaging and stamping phases. Throughout the color and clear coat stages, the machinery is monitored by a series of non-contact optical sensors. These sensors utilize light scattering techniques to evaluate the surface homogeneity and the gloss levels of the moving pencils. If a sensor detects a drop in reflection or a variation in color intensity, the information is relayed to the central control system, which can adjust the pump pressure or the conveyor speed to compensate. The mechanical regularity of this system is absolute, functioning with a degree of consistency that minimizes the human intervention required. The sound of the department is a symphony of industrial efficiency, the whirring of the extraction fans, the rhythmic clicking of the transfer arms, and the steady rush of air through the drying ducts. The state of the pencils at the conclusion of this chapter is one of aesthetic completion. The raw wood and mineral core have been completely encapsulated within a multi-layered polymer shell that is both durable and visually standardized. The pencils possess a reflective quality that catches the light of the facility as they move in their organized crates toward the next department. They are no longer mere components, they are recognizable products, awaiting only the final functional additions and the marks of their branding. The process moves forward with the same unyielding pace as the next batch of primed white rods enters the yellow lacquer reservoir, beginning the cycle of transformation once more. The continuity of the production line is a testament to the industrial logic that governs every movement within the facility, ensuring that the flow of material remains constant and the quality remains unvarying. The progression of the fully lacquered hexagonal rods into the final assembly stage marks the transition from surface aesthetics to functional modularity. Having attained their final chemical finish and undergone the necessary period of atmospheric stabilization, the units are retrieved from their storage racks by a systematic mechanical sorting system. This system utilizes a series of oscillating gates that allow only one pencil at a time to pass onto a transverse conveyor belt. The conveyor is equipped with a sequence of recessed lugs that cradle each pencil, maintaining a perfectly perpendicular orientation as the line moves toward the primary trimming module. The atmosphere in this section of the plant is characterized by a high-frequency acoustic environment generated by the rapid rotation of the cutting spindles and the constant rush of high-velocity air within the waste extraction ducts. The first mechanical operation in this sequence is the simultaneous trimming of both ends of the pencil. This is necessary to remove the irregular edges where the lacquer may have accumulated during the extrusion coating process and to establish the standardized length of the instrument. The pencils are clamped between two continuous reinforced rubber belts that exert a constant downward pressure, ensuring that no rotational movement occurs as they encounter the saw blades. These blades are circular discs of high tensile steel, their edges embedded with synthetic diamond particles. As the pencils pass through the cutting zone, the blades shear through the wood, the glue line, and the graphite core with a singular fluid motion. This action results in a perfectly flat vertical surface at each end of the hexagonal rod, exposing the dark circular cross-section of the lead against the pale cedar wood and the surrounding yellow lacquer. Immediately following the longitudinal calibration, the pencils proceed to the shouldering station, where the posterior end of the unit is modified to accept the metallic ferrule. This operation requires the transformation of the hexagonal geometry into a cylindrical tenon. The mechanical interface for this task consists of a rotating cutter head that encircles the end of the stationary pencil. Inside the cutter head, a series of small, precisely angled knives rotate at a frequency that produces a steady mechanical drone. As the cutter head advances along the axis of the pencil, the knives remove a specific depth of material from the hexagonal facets, carving a circular shoulder into the wood. The lignin and cellulose fibers are ejected in the form of microscopic curls and fine dust, which are immediately drawn into the vacuum system. The resulting tenon is a smooth, cylindrical protrusion that possesses a diameter slightly smaller than the main body of the pencil, terminating in a crisp 90-degree step where the hexagonal profile begins. The appearance of the tenon is characterized by the raw, unpainted wood grain, providing a tactile contrast to the high-gloss lacquer of the rest of the unit. The surface finish of this cylindrical section must be exceptionally uniform to ensure a proper fit with the metal component. While the pencils are being shouldered, the supply of metallic ferrules is managed by a secondary feeder system. These ferrules, small cylindrical caps manufactured from a malleable aluminum alloy, are stored in a large vibrating bowl. The vibration of the bowl facilitates the movement of the ferrules along a spiral track that lines the interior wall. As they move upward, a series of geometric gates ensures that only those ferrules oriented with their open end downward are allowed to proceed to the delivery chute. The sound of the ferrules in the bowl is a constant metallic clatter, a rhythmic shimmering sound that permeates the local environment. The ferrules are then moved end to end along a gravity-fed rail toward the assembly module. Before the metal cap is joined to the wood housing, a minute quantity of a fast-acting adhesive is dispensed onto the tenon. This adhesive application involves a precision-timed jet that releases a single droplet of the liquid onto the rotating wood surface. The liquid spreads through capillary action, wetting the wood fibers and preparing the surface for the chemical bond. The movement of the adhesive applicator is synchronized with the forward progress of the pencils on the conveyor, occurring with a mechanical regularity that minimizes any waste or excess. The scent of the adhesive, sharp and localized, blends with the persistent aroma of the cedar wood and the metallic tang of the aluminum components. The actual seating of the ferrule is a decisive mechanical event. A pneumatic plunger governed by a series of high-speed air valves captures a single ferrule from the end of the delivery rail and thrusts it onto the wood tenon. This movement is a quick, linear stroke that forces the metal cylinder over the wood until it meets the hexagonal shoulder. The internal diameter of the ferrule is designed to create a slight interference fit with the tenon, requiring a specific amount of force to ensure that the two components are fully integrated. The sound of the seating process is a repetitive pneumatic hiss, followed by a dull metallic click as the ferrule reaches its final position. This action is repeated for every unit in the line, creating a continuous flow of pencils that now feature a bright metallic cap at one end. To ensure that the ferrule remains permanently attached to the wood housing, the assembly passes through a secondary securement station. This involves the use of a set of radial crimping tools that descend upon the metal cylinder. These tools feature a series of hardened steel teeth that press into the aluminum, creating a permanent mechanical deformation. As the teeth converge, they pinch the metal into the soft fibers of the cedar tenon, forming a series of horizontal indentations or knurls that wrap around the circumference of the ferrule. This mechanical interlock prevents the ferrule from rotating or being pulled off during the stresses of future use. The movement of the crimping jaws is a short, powerful contraction, occurring with a mechanical, decisive force that resonates through the conveyor track. The quality of the ferrule attachment is monitored by an automated vision system and a series of mechanical probes. The vision system utilizes a set of cameras to verify that the ferrule is seated flush against the hexagonal shoulder and that the crimping pattern is symmetrical and complete. Simultaneously, a mechanical arm applies a calibrated tensile force to the ferrule of every 100th pencil to ensure that the adhesive bond and the mechanical crimp meet the structural requirements. If a unit fails to meet these criteria, it is automatically identified by the control software and removed from the line by a pneumatic ejector. This constant monitoring ensures that the flow of product into the next phase remains within the established technical parameters, preventing the accumulation of defective units. The pencils, now fitted with their metallic ferrules, are organized back into their oriented stacks. The addition of the metal cap significantly alters the physical appearance of the instrument, providing a bright, reflective highlight that contrasts with the deep yellow of the lacquer. The units possess a new center of gravity, shifted slightly toward the posterior end by the weight of the aluminum. They move toward the next module where the final functional component will be added. The atmosphere of the facility remains one of steady, unvarying production as the mechanical systems continue their repetitive cycles of trimming, milling, and assembly. The flow of materials is a constant river-like movement through the machinery, guided by the cold, logical sequences of the industrial controllers. As the crates are moved to the tipping department, the technical completion of the structural housing is achieved. The pencil now possesses its full longitudinal dimension and its primary metallic hardware. The transition from a simple wooden rod to a complex multi-component assembly is nearly complete. The processes described in this chapter, the high-speed sawing, the precision milling, and the pneumatic assembly, represent the final mechanical modifications to the wood housing. The instrument now awaits the insertion of the elastomer plug, a process that will finalize its utility as a reversible marking tool. The steady hum of the plant continues, a backdrop to the endless procession of yellow and silver units moving toward the terminal stages of their manufacture. The final functional modification of the writing instrument involves the preparation and integration of the elastomer component, commonly referred to as the eraser. This process originates in a specialized section of the facility dedicated to polymer chemistry and rubber compounding. The creation of the eraser begins with the introduction of raw synthetic elastomers, primarily styrene butadiene rubber, into a high-torque internal mixer. These raw materials arrive in the form of dense, pale-colored blocks, which are mechanically sheared into smaller fragments by the action of heavy, counter-rotating rotors. As the rotors turn, the mechanical friction generated within the mixing chamber causes a gradual increase in the temperature of the material, shifting the polymer from a solid state into a thick, viscous dough. This transformation is a slow, unvarying process, governed by the resistance of the molecular chains as they are stretched and rearranged by the heavy machinery. Once the polymer has reached the desired state of plasticity, a series of abrasive fillers and chemical additives are introduced into the mixture. These fillers, typically consisting of finely ground pumice and calcium carbonate, are essential for the mechanical function of the eraser, providing the necessary friction to lift graphite particles from the surface of paper. The powders are dispensed from overhead hoppers in a steady, controlled stream, falling into the mixing chamber where they are folded into the rubber matrix. The movement of the rotors ensures that the abrasive particles are distributed with absolute uniformity, creating a composite material that possesses a consistent density throughout its volume. The sound of the compounding process is a deep, rhythmic thudding that resonates through the floor of the mixing room, accompanied by the persistent hum of the cooling systems that prevent the rubber from reaching a state of premature vulcanization. The homogenized rubber compound is then discharged from the mixer and passed through a series of heavy rollers that flatten the material into a continuous sheet. This sheet is then fed into a cold feed extruder, a machine that utilizes a long rotating screw to force the rubber through a circular die. As the material is compressed within the extruder barrel, it is pushed toward the aperture, emerging as a continuous cylindrical cord. The surface of the cord is matte and slightly tacky, maintaining its circular profile as it is supported by a series of moving pulleys. This cord represents the raw form of thousands of individual eraser plugs, moving with a slow, unvarying velocity towards the vulcanization tunnel. The atmosphere in this area is characterized by the scent of warm rubber and the steady mechanical whir of the extruder motor. The vulcanization process involves the application of heat and pressure to trigger a chemical cross-linking of the polymer chains, transforming the soft rubber into a resilient thermoset elastomer. The continuous cord passes through a pressurized tunnel filled with saturated steam, where the thermal energy permeates the material and initiates the formation of sulfur bridges between the molecules. This chemical transition is essential for the durability of the eraser, ensuring that it remains pliable yet firm during the stresses of use. As the cord emerges from the vulcanization tunnel, it is immediately submerged in a sublimate cooling bath of treated water. The sudden change in temperature stabilizes the polymer structure, and the cord is then dried by a series of high-pressure air knives that strip the moisture from its surface with a loud, continuous hiss. The stabilized rubber cord is then moved toward a high-speed rotary cutting station. This machine features a thin, circular blade that rotates at a high frequency, lubricated by a continuous mist of water and silicone. As the cord is fed into the cutting zone, the blade slices through the elastomer with a repetitive mechanical rhythm, creating individual eraser plugs of a standardized length. These plugs are small, uniform cylinders, characterized by their smooth, flat ends and their consistent gray or pink coloration. The plugs are collected in large, vibrating bins where they are tumbled with a fine coating of powdered lubricant to prevent them from adhering to one another during storage and transport. The sound of the cutting station is a sharp, persistent clicking that occurs at regular intervals, marking the transformation of the continuous cord into discrete functional units. Simultaneously, the pencils, already fitted with their metallic ferrules, are moved into the tipping department. The eraser plugs are retrieved from their bins and loaded into a large vibratory bowl feeder. The vibration of the bowl causes the plugs to move upward along a spiral track, where a series of geometric gates ensures that they are oriented vertically as they reach the delivery rail. The sound of the eraser plugs in the bowl is a soft, continuous rustling, a subtle acoustic backdrop to the louder mechanical operations of the assembly line. The oriented plugs are then moved end-to-end toward the insertion module, where they will be permanently joined to the metallic housing of the pencil. The insertion of the eraser plug is a precision pneumatic operation. As each pencil reaches the assembly point, a pneumatic ram captures a single eraser plug from the delivery rail and forces it into the open end of the metallic ferrule. This movement is a quick, linear stroke that requires a specific amount of force to overcome the frictional resistance between the rubber and the aluminum wall. The plug is seated to a predetermined depth, ensuring that a portion of the elastomer remains exposed for use, while the remainder is securely anchored within the metal cap. The sound of the insertion is a rhythmic series of pneumatic pulses, a quick hiss followed by a dull thud as the plug reaches its final position. This action occurs with a mechanical regularity that defines the throughput of the final assembly line. To ensure that the eraser plug cannot be dislodged, the ferrule undergoes a secondary crimping or pinching operation. This involves the use of a set of radial jaws that descend upon the upper portion of the metal cylinder. As the jaws converge, they exert a powerful compressive force that deforms the aluminum, pressing it into the soft surface of the eraser plug. This creates a permanent mechanical interlock, forming a series of small indentations that hold the elastomer in place against both rotational and tensile forces. The movement of the crimping jaws is a short, decisive contraction, occurring with a mechanical finality that resonates through the assembly track. The resulting connection is a monolithic union of wood, metal, and rubber, marking the functional completion of the writing instrument. The quality of the eraser insertion is monitored by an automated vision system that utilizes high-speed cameras to inspect the height and alignment of each plug. The system verifies that the elastomer is seated correctly and that the secondary crimp has been executed according to the technical specifications. If a unit is detected with an off-center or improperly seated eraser, it is automatically identified by the software and diverted from the main conveyor by a pneumatic ejector. This constant inspection ensures that every pencil leaving the assembly line possesses a functional and securely attached eraser, maintaining the reliability of the product. The mechanical regularity of the insertion and inspection forms a continuous loop of production that mirrors the consistency of the earlier manufacturing stages. The pencils, now complete with their erasers, are organized into large, oriented stacks. The addition of the elastomer plug provides the final functional characteristic of the tool, transforming it into a reversible marking instrument capable of both creation and correction. The pencils possess a final standardized weight and a balanced center of gravity that is the result of the calculated integration of all their constituent parts. They move toward the final department of the facility, where they will receive their identifying marks and be prepared for distribution. The atmosphere of the plant remains one of steady industrial progress as the mechanical systems continue their repetitive cycles of synthesis, extrusion, and assembly. The flow of materials is a constant, unvarying movement through the machinery, guided by the cold, logical sequences of the production environment. As the crates of finished pencils are moved to the branding and packaging area, the technical evolution of the product is nearly finished. The instrument now possesses all its physical components, from the vitrified mineral core and the aromatic cedar housing to the high-gloss lacquer and the metallic ferrule with its integrated eraser. The processes described in this chapter, the compounding of synthetic polymers, the high-pressure extrusion of the rubber cord, and the pneumatic assembly of the tipping, represent the final stages of the pencil's physical construction. The instrument now awaits the final aesthetic and logistical marks that will define its presence in the commercial world. The steady hum of the facility continues, a backdrop to the endless procession of finished units moving toward the final realization of their industrial purpose. The progression of the functionally complete pencils into the final branding and packaging department represents the concluding stage of their transformation from anonymous industrial components into specific commercial commodities. This phase is initiated by the movement of the oriented stacks of pencils onto a high-speed transverse conveyor system, which aligns each unit with a precise orientation so that one specific hexagonal facet is facing upward toward the marking apparatus. The atmosphere in this section of the facility is characterized by the localized heat emanating from the thermal presses and a distinct acoustic environment composed of the rapid, rhythmic stamping of the dies and the high-frequency hiss of the foil advancing through the tensioning rollers. The mechanical regularity of this department is a display of synchronized timing, where the movement of the pencils is perfectly matched to the cycle of the branding machinery. The process of branding utilizes a method known as thermal foil transfer, which involves the permanent application of a pigmented or metallic layer from a carrier film onto the lacquered wood surface. This film, or foil, is a complex multi-layered material wound onto large plastic spools. It consists of a thin polyester base which serves as the carrier for a sequence of chemical coatings, including a release layer, a decorative layer of vacuum metallized aluminum or colored pigment, and a final heat-activated adhesive layer. The foil moves across the stamping zone in a series of incremental steps, controlled by a set of tensioning rollers that ensure the film remains perfectly flat and taut as it passes beneath the stamping die. The movement of the foil is a continuous, stuttering progression, advancing a few millimeters after each impact to provide a fresh area of pigment for the subsequent pencil. The mechanical heart of the branding operation is the heated metal die, which is manufactured from a dense alloy such as brass or hardened steel. The face of the die is engraved with the specific characters and symbols of the brand name, the model number, and the hardness grade of the graphite core. This die is mounted within a thermal press that maintains a constant elevated temperature through the use of internal electrical heating elements. The temperature is regulated by a feedback system that monitors the thermal state of the metal every millisecond, ensuring that the heat remains within a specific range necessary to activate the adhesive without damaging the underlying nitrocellulose lacquer. The sound of the stamping press is a sharp, repetitive thud as the die descends and makes contact with the pencil facet, a sound that repeats with an unyielding frequency throughout the production shift. When the heated die makes contact with the foil and the pencil, a combination of thermal energy and mechanical pressure causes the adhesive layer of the foil to melt and fuse with the lacquer. Simultaneously, the release layer of the foil is activated, allowing the decorative pigment to separate from the polyester carrier and remain fixed to the wood. This transfer occurs within a fraction of a second, during a period of dwell time where the die remains in its downward position. As the die retracts, the pencil moves forward and the branding is revealed as a crisp, metallic, or colored mark that is permanently embedded in the surface. The quality of this mark is a function of the equilibrium between the temperature of the die, the pressure of the press, and the specific chemical composition of the lacquer. Any deviation in these variables would result in a fragmented or blurred image, necessitating a cessation of the line for mechanical recalibration. Immediately following the stamping operation, the branded pencils pass under a high-speed machine vision system. This system utilizes a series of high-resolution cameras and stroboscopic LED lighting to capture an image of every branded facet as the pencils move along the conveyor. The software of the vision system performs a real-time comparison between the captured image and a digital master template, evaluating the sharpness of the characters and the alignment of the text relative to the longitudinal axis of the pencil. If the system detects a branding defect, such as a missing letter or an off-center mark, the specific unit is tracked through the system and automatically removed from the line by a pneumatic ejector. This constant automated inspection ensures that the visual identity of the product remains consistent, preventing any substandard units from reaching the packaging phase. The pencils that pass inspection move toward the collation module, where the bulk flow of individual units is organized into standardized retail quantities. This process is managed by a rotating star wheel mechanism, which captures the pencils one by one in a series of calibrated slots. As the wheel turns, it counts the pencils, gathering them into groups of 12. Once a full count is achieved, the group is shifted laterally onto a secondary track that leads into the cartoning machine. The movement of the star wheel is a steady circular rotation, accompanied by the soft clicking of the pencils as they are captured and released. This mechanical counting is a fundamental part of the organizational logic of the facility, transforming the continuous stream of product into discrete, manageable units. The packaging of the pencils involves the use of pre-printed carton blanks manufactured from a high-quality paperboard. These blanks are stored in a vertical magazine where they are retrieved by a set of vacuum suction cups and moved into the erecting station. The machine utilizes a series of mechanical lugs and folding arms to transform the flat blank into a three-dimensional box. As the box takes shape, the end flaps are held open to receive the collation of 12 pencils. The movement of the pencils into the carton is a single linear stroke, performed by a mechanical pusher that slides the group of units into the cardboard housing. The sound of the cartoning machine is a complex arrangement of vacuum hisses, the rustling of cardboard, and the mechanical clatter of the folding arms, all functioning in a synchronized loop. To seal the cartons, a small quantity of a thermoplastic adhesive is applied to the end flaps. This adhesive, often referred to as hot melt glue, is kept in a molten state within a heated reservoir and is dispensed through a series of precision nozzles. As the carton flaps are folded inward, the nozzles release a controlled bead of the liquid glue, which solidifies almost instantly as it comes in contact with the cooler surface of the paperboard. The scent of the hot melt glue is a subtle waxy aroma that lingers around the packaging module. The finished cartons are then moved through a final set of compression rollers that ensure a secure bond, resulting in a finished retail pack that is structurally stable and ready for distribution. For larger distribution requirements, the individual 12 packs are often subjected to a secondary packaging process known as shrink wrapping. In this stage, a specific number of cartons are stacked and wrapped in a thin, transparent film of polyolefin. These bundles pass through a thermal tunnel where the application of hot air causes the film to contract and tighten around the cartons, creating a secure, tamper-evident bundle. The movement through the shrink tunnel is a slow, unvarying progression, with the heat from the tunnel emanating into the surrounding air. As the bundles emerge, they are cooled by a series of fans, causing the film to achieve its final clear state. The resulting packages are then organized into larger corrugated shipping cases, which are sealed with adhesive tape and moved toward the palletizing station. The final mechanical event in the facility is the palletization of the shipping cases. This task is performed by a robotic arm that utilizes a vacuum-based gripper to lift the cases and place them onto a wooden pallet in a predetermined interlocking pattern. The movement of the robotic arm is a display of calculated geometric precision, shifting from the delivery conveyor to the pallet with a repetitive, fluid motion. Once the pallet is full, it is moved to a stretch wrap station, where a rotating platform spins the pallet while a roll of plastic film is applied, securing the entire load for the stresses of global transport. The pencils have now achieved their final state of organizational readiness, moving from the production floor toward the loading docks, where they will begin their journey toward the end user. The facility continues its unyielding operation as the next batch of pencils enters the branding press, beginning the final sequence of marking and collation once more. The final stage in the life cycle of the writing instrument begins with its departure from the production facility, transitioning from a state of manufacturing into a phase of global logistical transit. This phase is initiated as the palletized and stretch-wrapped units are moved from the warehouse floor into the hollow rectangular interior of an intermodal shipping container. The container, a steel structure designed for structural rigidity and atmospheric protection, is positioned at the loading dock, where a forklift executes a series of repetitive linear movements to fill the available volume. Each pallet is placed in a specific orientation to ensure the weight is distributed evenly across the floor of the container. The atmosphere in this area is a combination of the low-pitched roar of the forklift's internal combustion engine and the rhythmic thudding of the tires crossing the dock leveler. Once the capacity is reached, the heavy steel doors are closed and sealed, marking the end of the factory's direct physical control over the product. The transit phase involves the movement of the container through a variety of geographic and climatic zones, necessitating a state of internal atmospheric equilibrium. Inside the sealed steel environment, the pencils are subjected to fluctuations in temperature and humidity as the container moves across maritime and terrestrial routes. The incense cedar wood of the pencil housings, being a hygroscopic material, possesses a natural tendency to absorb or release moisture in response to these external changes. To manage this, the packaging includes desiccant packets that utilize chemical adsorption to maintain a stable moisture level within the secondary cartons. The transit on a cargo vessel is a period of slow, rhythmic oscillation. As the ship moves across the surface of the ocean, the steady vibration of the massive engines resonating through the stacked containers. This period of transit is a state of suspended animation, where the pencils remain organized in their crates, isolated from the external world. Upon arrival at a regional distribution center, the container is opened and the pallets are retrieved for storage in high bay racking systems. The distribution center is a cavernous, climate-controlled environment where the movement of goods is managed by automated systems and computerized tracking. The pencils are stored in a state of high-density organization, awaiting the signals that will trigger their movement toward retail outlets. The environment here is characterized by the hum of the ventilation systems and the occasional high-pitched whine of an electric reach truck as it retrieves a pallet from the upper reaches of the steel racks. The organizational logic of the warehouse ensures a consistent flow of inventory, utilizing a system where the oldest units are moved first to maintain the stability of the elastomer erasers and the adhesive bonds. The final realization of the pencil's functional purpose occurs in the hands of the end user, initiating a process of controlled, iterative mechanical degradation. The first functional event is the sharpening of the instrument, which involves the removal of the protective lacquer and the cedar wood to expose the marking core. When the pencil is inserted into a sharpener, a set of helical blades or a single tensioned steel knife begins to rotate around the longitudinal axis of the unit. The blade shears through the wood fibers and the vitrified graphite, creating a continuous, spiraling shaving that is ejected into a collection chamber. This action creates a conical tip, with the graphite core tapering to a fine point. The sound of the sharpener is a grinding, rhythmic vibration that reflects the resistance of the wood and the mineral core to the steel edge. The act of writing is a physical interaction between the graphite clay core and the surface of a marking medium, such as paper. As the user applies a vertical force and moves the pencil across the page, the friction between the tip and the cellulose fibers causes a process known as exfoliation. At the microscopic level, the weak intermolecular forces within the graphite allow layers of carbon flakes to slide off the core and become embedded in the texture of the paper. This transfer of material is a steady, incremental process that results in a visible gray-black mark. As the graphite is deposited, the point of the pencil gradually blunts, requiring a subsequent sharpening cycle to restore the conical geometry. The writing process is a silent, unvarying sequence of friction and deposition, a mechanical recording of the user's movement. The eraser plug, integrated into the metallic ferrule, serves as a secondary functional component designed for the mechanical removal of the graphite marks. When the user applies the eraser to the paper with a back-and-forth motion, the friction generates heat and causes the synthetic elastomer to deform. The rubber matrix of the eraser undergoes a process of controlled shedding, where small fragments of the elastomer break away, capturing the graphite flakes and lifting them from the paper fibers. This action results in a collection of small, rubbery crumbs that are brushed away from the surface. The eraser gradually reduces in volume with each use, its cylindrical profile becoming rounded and worn as it fulfills its purpose of correction and refinement. The life cycle of the pencil is defined by this progressive reduction in its physical dimensions. Each sharpening cycle removes a few millimeters of the wood and core, and each act of writing depletes the graphite matrix. The instrument becomes shorter over time, its center of gravity shifting towards the posterior end as the weight of the wood and lead is lost. The ergonomic utility of the pencil is eventually compromised when its length becomes insufficient for a stable manual grip. At this point, the pencil is reduced to a stub, a short section of cedar wood, the metallic ferrule, and the remains of the eraser plug. The instrument, which began as a monolithic block of mineral and biological matter, has been largely converted into shavings and graphite marks. The final state of the pencil involves its disposal and the subsequent environmental breakdown of its remaining components. The incense cedar wood is a biodegradable material that will eventually return its carbon to the earth as it is broken down by microbial activity. The graphite core, being a stable form of carbon, remains chemically inert, existing as a harmless mineral fragment within the soil or the landfill. The metallic ferrule, however, is a more persistent component. The aluminum alloy will eventually oxidize over a long period, but it retains its metallic form for many years unless subjected to mechanical recycling. The entire process, from the slow growth of the cedar tree and the geological formation of the graphite, to the industrial assembly and the final act of writing, is a closed loop of material transformation. The energy and precision invested in the manufacturing stages are ultimately realized in the simple, silent marks left on a page. The pencil is a tool of profound reliability, functioning without the need for an external power source or complex electronic interfaces. Its mechanical simplicity is the result of centuries of industrial refinement, ensuring that the movement of the hand is translated into a permanent record with absolute consistency. The story of the pencil concludes with its disappearance, its substance having been distributed across countless pages and collected in the dust of sharpeners and erasers. The atmosphere of the facility where the story began continues to hum in the same unvarying regularity as new batches of wood and mineral move through the machinery. The departure of one container is immediately followed by the arrival of another, maintaining a continuous cycle of production and distribution. The industrial logic of the facility ensures that for every pencil that reaches the end of its life, several more are being formed in the presses and coating modules. The process is a testament to the endurance of mechanical engineering and the steady, monotonous rhythm of the production environment, which continues to turn the raw materials of the earth into the simple, functional objects of human civilization.